So in the previous lecture, we were talking about Laplace transform. We motivated the discussion by stating that for many signals, exponential signals, particularly signals that are growing exponentially, you cannot really take Fourier transform because they are not integrable signals. However, Laplace came up with the idea that let's, instead of taking the Fourier transform, let's discount the signal using e raised to minus sigma t term, and then the overall signal would become absolutely integrable, and therefore we could take the Fourier transform of that, and this entire process is known as Laplace transform, right? So where did we talk about Laplace transform? Right here. Okay, so this is where, so you can take the Fourier transform of xt multiplied by e raised to negative sigma t, and this is termed as Laplace transform, where S can take any complex value. So S can be uh, of the form S equals to sigma plus j omega. So S can be pretty much any complex number. What is wrong with the pen? Yeah. Okay. Then we talked about inverse Laplace transform. So you go from the signal, which is a function of time, to a function which is a function of complex number, which is the Laplace transform. So how do you go back from the Laplace transform back to the original signal? So we came up with a expression for inverse Laplace transform that's given here. And then we talked about two specific examples. One is an exponential signal. Um, and we found what the Laplace transform of this exponential signal is. It's 1 over s minus a for real values of s greater than a. And then we did another example of um, a similar looking signal, but with u minus t. So the signal was active all the way from minus infinity to 0, and after that the signal became inactive. So the signal was 0 after time t greater than 0. So let's write down the Laplace transform for both these signals together, and let's begin the discussion for today's lecture. So example 1 was my xt is e raised to negative at ut, and the Laplace transform was 1 over s plus a. So I'm making a small change. So um, in the example, I had e raised to at, but right now I'm using e raised to minus at. So just replacing a with negative a. And the region of convergence was that real part of s should be greater than negative a. Example 2 was xt equals to minus e raised to minus at u minus t. And the Laplace transform is the same function, 1 over s plus a, but the region of convergence is real part of s is less than negative a. Okay, so region of convergence matters. Okay, so even though two signals have the same Laplace transform, the functional form is the same, but because the region of convergence are different, you can see that there is a difference in the signal itself. So this signal, the first signal, let me say x1t and x2t. So the first signal looks like this, whereas the second signal, oh, this looks something like this. This is my x2t. Okay, so the two signals are quite different, and therefore even though the Laplace transform looks the same, because of the region of convergence, um, the two signals are actually completely different, as you can see from the figure of the two signals. Okay, so this is the most important concept that I want you to remember. Two signals can have the same Laplace transform, but how the signal would look depends largely on the region of convergence. And this is an example for that. Okay. Any questions so far?
Are you using the notation RE as real, or are you using that for a region of convergence?
So this is, okay, so RE is real part of S,
Okay.
but the region of convergence would be, let me write the region of ROC
Okay, so we would use ROC like in my last class. Okay.
greater than negative A. Yeah.
That makes sense.
Yeah. Okay, let's look at, we'll continue to look at many examples right now, because I want you to become very comfortable with this notion of Laplace transform and how do you compute it. Let's look at example 3, and I'm going to pick e raised to negative t ut minus e raised to negative plus e raised to negative 2t ut. So I know that what would be the Laplace transform of the first term? So I have two terms here, right? Both are getting added.
The Laplace transform of the first term, wouldn't that just be 1 over S plus 1?
Right. And what's the region of convergence?
S has to be greater than -1.
Perfect. Yeah. And in this case, what about the second term? So you don't answer. Let me, someone else should answer this question. What about the second term? What's the Laplace transform of the second term?
1 over S plus 2.
Perfect. What about the region of convergence?
Greater than -2.
Perfect. Yeah. Okay. So now we have this sum of two signals, x1t, whatever, x3t is e raised to negative t plus e raised to negative 2t. And I know the Laplace transform of individual signals. So what do you think should the Laplace transform of the joint signal be? What should be x3 of s?
Really quickly, if instead of a -t or a -2 in the exponent, would we say, if it was a positive t and a positive 2, would we say 1 over S minus 1?
No,
No?
no. Yes, right. Okay, let's do that example as well. So if this was e raised to t ut plus e raised to 2t ut, let's write down what the Laplace transform is. For this one, it's 1 over s minus 1. Real part of s is greater than 1. For this term, it's 1 over s minus 2. Real part of s should be greater than 2.
Okay.
Okay. So this is just the individual term. So now we want to figure out what the Laplace transform of this overall sum should be. So let me call it x4, just so that the two signals are distinct. Okay, so let's look at x3 of t. What should the Laplace transform of x3 look like? So the summation is rather easy to do. It should be 1 over s plus 1 over 1 over s plus 2. And we will talk about the additivity property of Laplace transform at some point of time, but let's assume for the time being that we we know that Laplace transform is additive, and proceed with that assumption. So I'm just going to add the two functions, 1 over s plus 1 plus 1 over s plus 2. But remember that when we are talking about Laplace transform, the function is one part, but the second part is the region of convergence. So I need to figure out what the region of convergence should be. Anyone has any thoughts on what the region of convergence should be?
Would it be, between -2 and 1?
-2 and 1. Okay.
-1, I mean, between the two that we already have.
Right. Okay, let's think about it. How should I do it? Okay, well, okay, let me do it here. So I have -1 here. I'm going to, so this is my region of convergence for 1 over s plus 1. -2. This is my region of convergence for 1 over s plus 2. So what would the region of convergence for this sum be? So I can pick any point s in this set, capital in this region of convergence, and the function would be well defined with it with that particular value of s. So now when I'm summing up the two Laplace transforms, I want to make sure that for every s that I pick in the region of convergence, the Laplace transform should be well defined.
Would it be real of s is greater than -1?
Yeah, so it would be real of s greater than -1. And the reason, so this is intersection of the two region of convergence. So if you look at any point s such that real part of s is greater than -1, let's pick an s here, or let's pick an s here. So I know that this s also lies in the region of convergence for the second signal. So 1 over s plus 2, right? So this s is perfectly fine. Now, one suggestion was, what about s between -1 and s between -2 and -1? So let's pick an s here, which is between -1 and -2, right? So it's right of -2, but it's left of -1. And if you look at this particular point s, then the first term is not defined at that s because that's not part of the region of convergence, whereas the second term is defined there. So unfortunately, we can't really take that s. That s cannot be the part of the region of convergence because the first term is undefined at that particular point s. Okay, now let's consider an s which is left of -2. So so it's left of -1, and both the functions 1 over s plus 1 and 1 over s plus 2, both of them are undefined in this region, and therefore this s cannot be part of the region of convergence. So that's roughly the argument why when you sum two signals, then the Laplace transform will of course be the sum of individual Laplace transforms, but the region of convergence will be the intersection of the two region of convergences. Any question on this concept? Okay. Now, making the same argument in this case, we can argue that the Laplace transform of x4 would be 1 over s minus 1 plus 1 over s minus 2. And the region of convergence should be real part of s greater than 2. Because this region of convergence is contained in this region of convergence and in this region of convergence. So it's the intersection of the two region of convergences.
And if for the second term you had e to the negative 2t, or
This one?
yeah, I'm just trying to think, like, is there any way to have the region of convergence in a range?
Oh yeah,
So, like,
there will be a case where the region of convergence will be in the range. So that's my example 5. Or
okay,
sorry, example
gotcha.
6. So we have done
Gotcha.
1, 2, 3, 4. Let's do 5 and then we'll talk about in a range part.
Perfect.
Okay, so let's look at example 5. So this example is x5 of t is e raised to negative at cos omega t ut. No, omega is already used. I need to put some other number here. Let me just put bt. Okay, that's fine. Okay, a and b are some constants. Now we need to find the Laplace transform of this signal. So what do we do? Let's do the Euler relationship. So I can write my x5 of t as e raised to negative at e raised to b jbt plus okay, it looks correct. Okay, so we talked about the Laplace transform of e raised to negative at ut, but we haven't talked about Laplace transform of e raised to negative a plus jb t ut. Oh, I have to multiply it by ut everywhere. So let's try to use the first principle to compute the Laplace transform of just one of these signals. So let's pick this signal and let's try to find the Laplace transform of this signal. Let me call it yt. So y of s should be minus infinity to infinity e raised to negative I'm going to write S as sigma plus j omega for the time being. Now, as usual, whenever we see a term like ut in the expression, the first thing we do is just change the limit of the integral. So let's do that. 0 to infinity. Any questions until now? Okay, so I'm going to go back to our question. When is this integral absolutely integrable? When is this integral absolutely integrable? Sigma should be, or let me just write it. So the answer is when a plus sigma is less than 0. No, a plus sigma is greater than 0 because there is a negative sign already in front, which means that sigma should be greater than negative a, which means that real part of S should be greater than negative a. Okay. Everything looks good so far. Now, once I have picked my S such that real part of S is greater than negative a, I know that this integral makes perfect sense. So I can integrate it from 0 to infinity. And once I integrate it, what do I get? I get e raised to negative a plus jb plus s over negative a plus jb plus s 0 infinity t. So that's my integral for real part of s greater than negative a. And once I do the limit and all that stuff, what I would get is 1 over s plus a plus jb. This is my y of s. Okay. Any questions so far? Is the integration step clear to everyone? Okay, perfect. So let's look at example 1 and this particular example again. So if my signal is e raised to negative at ut, the Laplace transform is 1 over s plus a, real part of s greater than negative a. And if my signal is e raised to negative a plus jbt ut, then my Laplace transform is 1 over s plus a plus jb, real part of s greater than negative a. Okay, so there's quite a bit of similarity between the two Laplace transforms. So I replaced a with a plus jb in the second expression, and I replaced in the denominator a with a plus jb. So actually it looks pretty similar, and the region of convergence essentially is not changed at all. It's the same. Okay. Now let's go back to the original question we were interested in, which is the Laplace transform for x5 of t. So let's go down further. So my x5 of t was e raised to minus a minus so my Laplace transform is going to be 1 over 2 1 over s plus a minus jb plus 1 over 2 1 over s plus a plus jb. Okay. Any questions on this particular example, fifth example? Let's go to the sixth example. And this is again an exponential signal, but a very peculiar kind of exponential signal, e raised to negative b absolute value of t. T is in R. So this signal looks as follows. So I'm going to plot for b less than 0. Looks like a mountain. This is b less than 0. This is b greater than 0. Oh, I'm sorry. I think it should be the other way around. This is b greater than 0. This is b less than 0. Because of the negative sign, When b is positive, it decays exponentially, and when b is negative, it grows exponentially fast. So this is the situation where the region of convergence will actually be a strip around parallel to the j omega axis in the S plane. Let's look at any question? No? Let's look at the case of b greater than 0. So I'm going to write x of t as e raised to negative b absolute value of t. So I'm going to write it as e raised to negative bt ut, e raised to bt u minus t. Now let's apply example 1 and 2. We notice the following. The Laplace transform of this term is 1 over s plus b. Region of convergence is real part of s greater than negative b. For this case, the Laplace transform is negative 1 over s minus b. Okay, there is a question in the chat box. Let me get to that question in maybe a couple of minutes. And here the region of convergence is real part of s is less than b. Okay, and b is positive. B is positive in this case. So overall, the Laplace transform in this case, x5 of s is given by 1 over s plus b minus 1 over s minus b. And what is the region of convergence? This is negative b less than real part of s less than b. Okay, so I want the region of convergence is real part of s greater than negative b and real part of s less than b. So that makes it real part of s should be between negative b and positive b. Okay. Now, before I jump to the case of b less than 0, let me answer a question that is on the chat, which is what's the region of convergence for the previous signal? So here the region of convergence is real part of s greater than negative a. Sorry, I hadn't written it here. Please make a note, the region of convergence for x5 of s is real part of s greater than negative a. Okay. This is sixth example. So let me write 6 all over the place. X6, X6, X6. Okay. Perfect. So no questions so far. Let's talk about the case, the seventh example, which is b less than 0. X7 of t, b is less than 0. So this is negative bt ut plus e raised to bt u minus t. Now everything is going to be the same. So I'm just going to write the same thing again. This is 1 over s plus b. Real part of s should be greater than negative b. For this, the Laplace transform is minus 1 over s minus b. Real part of s is less than b. And I want you to remember b is less than 0 for the computation. What do you think would the region of convergence be in this case? Let's give b a specific value. So b equals to -1. So when b is equal to -1, this means that real part of s should be greater than 1, and this means that real part of s should be less than -1. So what values of s would satisfy these two constraints?
There wouldn't be one, would there?
Right. So there is no value of s which satisfies the two conditions simultaneously. So therefore, Laplace transform does not exist. So we can't take a Laplace transform for this particular signal because there is no value of s for which the region of convergence is the same for both parts of the signal. Region of convergence is an empty set. So this is one of those pathological signals for which the Laplace transform does not exist. Now, we don't particularly care about it because such signals are not commonplace in reality. We don't really see such signals in reality. Therefore, Laplace transform works for almost all the cases. But it's still a good mathematical exercise to understand what kind of signals do not admit Laplace transform. Okay. So what we have done is we have looked at the Laplace transform of a bunch of exponential signals, right? So, and what we have noticed in all these examples, so we talked about example 1 through 7, and in all these examples, assuming the Laplace transform exists, we have noticed that exponential signals have rational Laplace transform. Okay, so the first thing we noticed is exponential signals have rational Laplace transform. So that's number one. Number two, we have a region of convergence for every Laplace transform. For these signals for which Laplace transform exists. So whenever we talk about a rational Laplace transform, you can typically write it in the following form. X of s would be s plus z1, s plus z2, s plus zm over s plus p1, s plus pn. And z1 to zm, these are called zeros. No, I think negative z1 to, what should I do? Let me write negative z1 to negative zm. These are zeros of xs. So the roots of the numerator polynomial are called zeros of the Laplace transform x of s, and minus p1 to minus pn, these are called poles of xs. So the roots of the denominator polynomial are called poles of the Laplace transform. Now, whenever we talk about zeros and poles of a Laplace transform, we would typically represent them in the complex plane, which is called the S plane. And we will represent the poles with crosses. So this is minus P1, this is minus P2, this is minus P3, this is minus P4. So all the poles are represented by cross, and all the zeros are represented by small circles. This is negative Z1, this is negative Z2, this is negative Z3, and so on. Oh, I have to write this is imaginary axis and this is the real axis of the complex plane. And this S plane is essentially just a complex plane. So what I'm saying is we have a Laplace transform because the original signals are exponential. The Laplace transform is a rational function of S. A rational function of S can be written in this particular format, in this format. And the roots of the numerator are called zeros. The roots of the denominator are called poles. And if you look at the complex plane, which is called the S plane in the context of Laplace transform, you represent zeros with small circle and you represent poles with a small cross. Okay, so these are the poles and zeros of this Laplace transform x of s. Okay. Now let's talk about the region of convergence and how do we show the region of convergence. Actually, I've already showed you how region of convergence is shown. So let's consider the signal x of t equals to e raised to negative at ut, for which the Laplace transform is 1 over s plus a, and the region of convergence is real part of s greater than negative a. So this is the real s, this is the imaginary s, this is my s plane. I have a pole here. I have no zeros in this rational polynomial. I have a pole, negative a. Now, how would I represent this real part of s greater than negative a? I am going to draw a dotted line which is parallel to the imaginary axis, and it passes through the pole negative a. And then I'm just going to shade this region. This is the region where real part of s is greater than negative a. This is how we represent the region of convergence. It's important that you draw the dotted line here, because the dotted line would represent that this particular line is not included as part of the region of convergence. If it was a solid line, not a dotted line, then that line is included in the region of convergence. But as we mention here, I want my real part of s to be strictly greater than negative a. So therefore, this line has to be a dotted line, not a solid line. That's just the convention in mathematics. I'm not sure if you've seen it in some other math class, but typically that's how we represent. I think even in math textbook, if you're using a complex analysis textbook or something, if the boundary is not included as part of the set, then the boundary will be in a dotted shape. Just the mathematical convention. Let's
So I have a quick,
go ahead.
sorry, I have a quick question. On the previous example, when you had the rational Laplace, yeah. So would it be, would the region of convergence here be 0.3 greater than negative P3?
You are, so it really depends. I'll get to it probably in the next class. So it depends on whether the signal is starting from a point and then going all the way to plus infinity, or whether the signal is going from minus infinity and stopping at a certain point in time. So that, let's get to the second example, okay? And I'll get
good.
back to it. So my second example was xt equals to minus e raised to negative at u minus t. And in this case, the Laplace transform was 1 over s plus a, but the region of convergence was less than negative a. So this was my example 2. And this is my real, this is my imaginary, this is my S-plane, the usual stuff. This is my pole, negative a. Now negative a is not included as part of the region of convergence, so I'm going to draw a dotted line. But now the real part of S must be less than negative A for this signal, and that's why I'm going to shade this region where real part of S is less than negative A. Okay. So we see that in example 1 and example 2, there is a very peculiar phenomena where the Laplace transform is the same, but the region of convergences are quite different. So I just want to introduce two different types of signal, which is the examples are example 1 and 2. So one is the right-sided signal. So this is x of t equals to 0 for all t less than some t1. So this would look like this is my t1, this is x of t, this is t, and the signal looks like this. This is a right-sided signal. Okay, and an example is e raised to negative at ut, or e raised to negative at cos bt ut. So these are all right-sided signals. Okay. Now let's look at left-sided signals. I'm sure you're not surprised at the definition. So these are signals where xt equals to 0 for all t greater than t1. And so t xt, this is some t1, and my signal looks like this. So this is a left-sided signal, and the example of a left-sided signal is e raised to negative at u minus t. So because of this u minus t term, the signals are non-zero for all time t less than 0. And then after that, the signal becomes 0. So after t equals to 0, the signal becomes 0. That's because of this u negative t term in the signal. So these are known as left-sided signal. And what we noticed in the examples so this is a right-sided signal. And in the right-sided signal, the region of convergence is on the right side of the pole. Okay, so this is the property of a right-sided signal, whereas this is a left-sided signal. And in this case, we see that the property of the region of convergence is that it is on the right side of the on the left side of the pole. So the pole is negative a, and the region of convergence is on the left side of the pole. Okay, so that's probably, I mean, that probably gives you a intuition about why it's called a right-sided or a left-sided signal. And so today's class is over. In the next class, we'll talk about properties of region of convergence based on some of these intuition we have developed in today's class. And then we'll talk about properties of Laplace transform. So that's the topics for the next class. Thank you for your attention. See you on Friday.